Swayam Prabha. Digital India. Educated India.
I mentioned that due to the way the gel structure is created, it is based on nanometric particles, and between the particles that are bound chemically together, there is porosity, typically mesoporosity rather than microporosity. And it is interesting to see that the volume and the size of the pores can be modified by changing the amount of water that you have in your system, or the type of alkali cations and the curing temperature. So there are different ways in which you can affect the specific surface area. Here you can see some of our experiments. We can reach up to actually 180 square meters per gram by controlling these fabrication parameters. And here you can see, for instance, by modifying the curing temperature, we can increase the significantly, for the same formulation, the specific surface area. So I will be talking first about material extrusion, and then I will be talking about binder jetting. So you already know what direct inviting is. In the case of geopolymers, you have to realize that the setting reactions are quite fast, and this poses a challenge because it is a reactive mixture with a time-dependent rheology. So when we print, for instance, we print in surrounding the syringe with ice in order to keep the temperature down and allow for a printing window that can be up to 3 hours. And the ink should behave as a shear thinning will yield stress fluid. I already mentioned that. And I told you that geopolymer gels, especially at the beginning of the reaction, are reversible gels. So if you apply stress, you break the bonds. And when the stress is released, the bonds reform. But this type of behavior is not fully suitable for creating suspended structs. And since we are interested in using this approach for making filters, we need to be able to obtain that type of microstructure. So at the beginning, we modified the rheological behavior of geopolymer slurries using some additives such as polyacrylic acid and polyethylene glycol. And you can see that we were able to achieve better behavior, especially with PEG. And you can see the experiments for the recovery of the viscosity with time. The recovery is not yet ideal, but with these additives, it is improved. So 1 order of magnitude increase in G prime in about 10 seconds. So we worked a little bit for some time with this approach. And here we want to simply to investigate the effect of total porosity on the strength of the structures, materials with the same morphology. And you can see that, of course, by increasing the the porosity, you reduce the strength. Another thing that we looked at was the phase evolution and the mechanical properties of the components with increasing firing temperature. And you can see that when you go to 500 degrees, the material turns black because we have some residual carbon that is not being fully oxidized. The carbon comes from the PEG additive that we added. If we increase the temperature, we have a slight increase in open porosity. And if we look at the strat surface, we have the formation of some pores. We have a strong increase in strength with increased firing temperature because of the consolidation and ceramization of the material. And the material starts as inorganic, but the mesopores start closing and you obtain a dense matrix. And with increasing temperature, we found that we had a decrease in strength due to the formation of cracks induced by the crystallization of the material. We can make large samples. We also worked on making porous struts in order to allow for the media to like gaseous or liquid media to enter into the structure, interact with the geopolymer. So we realized that despite having this rheological additive, we still had issues in terms of the yield strength. And bear in mind that we were the first ones in the world to carry out this work, so we couldn't rely on other people's experience. And so we started adding some fillers, for instance, sand, in order to increase the yield stress. And you can see that in this way we can control the sagging of the structure for inclined planes. So having adding solid particles to the geopolymer helps. But if you want to use the geopolymer as a reactive and active material, then taking away some of the geopolymer and adding inert materials such as sand is not favorable. So we developed an approach where we generated geopolymer particles with the same composition of the surrounding matrix. And since they were solid, they contributed to the optimization of the rheology of the slurry. So, and of course, we can do that with both sodium-based or potassium-based materials. You can see the particles here more clearly. And this allows to have a very good retention of the shape of the scaffold. So these were our early experiments. We also started trying to make composites, here with carbon fibers, here with polymeric fibers. And polymeric fibers for geopolymers are more interesting because they can allow a degree of ductile fracture that inorganic fibers don't allow. The problem with polypropylene fibers is that they are, well, of course, commercially available. They're used to reduce the shrinkage, for instance, in mortars, and they can withstand a highly alkaline environment, but their length is quite high. 6 millimeters is the minimum that you can purchase. And this leads to the fact that it is difficult to have a large volume of fibers inside the material. So typically we cannot put more than 2, maximum 3% of these fibers inside the slurry. Otherwise the ink will clog the nozzle. We are interested in lattice structures, and I already demonstrated with pre-ceramic polymers, if you remember, that by modifying the assemblage of the layers, you can modify the mechanical strength and the permeability of the components. So we demonstrated that. We confirmed that also with geopolymers, and the results followed the same trend as already demonstrated. One of our PhD students started working on printing paths. I told you that with direct inviting, you need to the tip needs to follow a continuous path because it is virtually impossible to work with a start and stop approach. And this gives you some limitations in terms of the structures that you can print, but it also provides some opportunities. So he has been working on generating structures using fractal geometries. And these provide some advantages in terms, for instance, of permeability with respect to scaffold structures without compromising the strength. And you can see here a tomography reconstruction of a structure. In this case, it was not a space filling curve, but it was based on twisted scaffolds, and you can see the complex porosity inside that can be optimized for providing, for instance, mixing of different fluids. So on one side, using additive manufacturing, we can manipulate the macro porosity at any level, meaning that we can modify the amount of macro porosity, we can modify the size of the macro porosity, we can modify the geometry of the macro porosity. But we are interested in functional components where a fluid interacts with a solid material. So in order to favor that, we try to increase the mesoporosity, as I described, by modifying the processing conditions. And once we have this type of components that possess macro porosity and mesoporosity, then we can start using them, for instance, for water purification and from ammonia or from metals or pharmaceuticals present in water. And we also use these materials for biodiesel catalysis, as I will show you in a moment. So when we started this work and we were trying to use geopolymer as a active material for absorbing cations by ion exchange from water to eliminate pollutants from water, we realized that using PEG was a good approach for fabricating structures with the geometry that we wanted. But if we looked at the BET, so the specific surface area of such materials, we found that PEG would block the mesopores. So we tried calcinating, we tried washing, but with this approach, we were never able to obtain a very high specific surface area. This is still good enough for some applications, especially if they are based on ion exchange. But of course, we wanted to do better, and I will tell you later how we improved the results. I mentioned that we wanted to use these components for removal of pollutants from water. In this example, I'll show you some experiments that we carried out in collaboration with some colleagues for eliminating ammonium ions from water. And you can see that we were quite successful, and the material kept a reasonable performance after a certain number of cycles. Besides these data, what is interesting is that we tested our material versus other materials that have been proposed for the same application, and specifically active carbon and granulated active carbon. And these materials, of course, work well, but they are either in powder form or in granules. And if you look at the pressure drop provided by a powder bed or a bed or containing granules, you can see that the powder bed has a very high pressure drop. The granules have a better performance, and that's why they make them. But it still has some significant pressure drop. And the advantage of additive manufacturing is that you can create components that have a much lower pressure drop. So at least 2 orders or 1 or 2 orders of magnitude lower than competing materials. So this is very favorable for practical applications. Another thing that we explored is the use of the alkalinity in the geopolymers for making biodiesel. So as you're certainly familiar, in order to make biodiesel, you start from vegetable oil, methanol, and you have a homogeneous catalyst, typically sodium hydroxide, which is dissolved into the system. So it's a homogeneous catalyst. And this approach works well. You have the formation of biodiesel plus glycerol that then can be separated due to the difference in density. The problem with this approach, which is the normal one, is that it is difficult to separate the catalyst from the biodiesel for purification. You need to wash the biodiesel several times in order to reduce the content of sodium hydroxide below a certain level. So we thought that if we use the geopolymers, that we could use the geopolymers since they have provide a very high pH as a heterogeneous catalyst, with the advantage that you can simply then remove the solid from the liquid and you have no separation problems. And if you're familiar with biodiesel production, you know that there are a lot of different reaction conditions that you can modify: the temperature, the contact time, the amount of catalyst, and the percentage of excess of methanol. So there is a wide range of processing parameters that can be, or reaction parameters that can be modified. We didn't test all of them. We carried out the experiments in what we thought were the best possibilities. We worked with colleagues from Brazil for this work, and we used soybean oil as a source of triglycerides. And you can see that the system worked. We were able to generate biodiesel plus glycerol. And in terms of the yield is certainly below the yield that one expects from commercially available approaches. But as I mentioned, we didn't try to further optimize the reaction. We wanted to demonstrate that you can use this approach. You can certainly comment, you should comment on the fact that how can we be sure that this is heterogeneous reaction, not a homogeneous reaction, because the alkaline ions in the geopolymers are mobile, so they could be transferred to the ion exchange transfer to the biodiesel system. And we carried out, of course, analysis of the biodiesel, and we saw that the content of sodium was below the threshold that requires the purification, despite using the same amount of catalyst that one would have used if the system was catalyzed using a homogeneous catalyst. So this proved the fact that we had a very limited release of sodium into the system. Okay, so we can, I didn't mention one thing. So here you certainly want to have also a decent mesoporosity. So what we did was that we started using clay, for instance, bentonite, as a rheological modifier for the geopolymer. So we got rid of the PG, which blocks the mesopores, and now we use a certain amount, I think 10 to 20% of clay, which provides a very suitable way of controlling the rheology. And clay does not bother us because we are using the components at room temperature. They are not fired, so there's no decomposition of the clay. So we can exploit the macroporosity by CAD design. We can exploit the mesoporosity by playing with the composition of the geopolymer and different other features. But we would like also to have additional specific surface area and behavior. So one thing that you can do is that you can add some fillers that have microporosity. And of course, such fillers could be active carbon, which is very stable inside the geopolymer, or could be zeolites. Not all zeolites are chemically stable inside a geopolymer because of the high alkalinity, but a wide range of zeolites are. So we started adding microporous fillers in order to further enhance and modify the behavior of the material. And I would like to point out the fact that we can do that and it works because the matrix of the geopolymer matrix contains 40% of mesoporosity. And this leads to a wide volume of interconnected porosity that allows for the access to the to the fillers with the micro porosity. If we had a dense matrix, of course, this approach wouldn't make sense, but we have a permeable matrix. So we tested for some applications. As you might have gathered, we work mainly on shaping manufacturing of components rather than testing them. So we need to collaborate with people that have these capabilities. Here we simply used chabazite, which is a zeolite. This is very cheap and comes from simply digging up from the ground. And the powder is very fine, so we have a limit as to the amount that we can add. Typically, this limit is about 60 weight percent with respect, which is similar to the volume percent with respect to the geopolymer matrix. But we also need some matrix to provide strength. And you can see that the chabazite was not decomposed in contact with the geopolymer, and adding, if this is the base geopolymer, by adding chabazite, we have gained all this micro pores, and therefore we have a much higher specific surface area. We added also activated carbon, and we compared the behavior of geopolymer microbeads that we generated with 3D lattices, and the behavior was better for the lattices with respect to the microbeads, or with respect to the geopolymer by itself. We also added the SM5 zeolite. This is one of the zeolites that can remain stable inside the material. With 60% zeolite, we can go up to 250 square meters per gram. We carried out acid treatment, ion exchange of the sodium ions in the zeolite with copper. And we looked at the NO conversion, nitrous oxide, and at temperature as low as 150, we were able to reach a conversion of 100% with a very good selectivity. So this approach is nice. We also, I mentioned to you that geopolymers are considered cryptocrystalline materials, meaning that they have a composition similar to that of some zeolites, and the formation of zeolites can be triggered, typically by temperature and humidity. And we found one composition of geopolymers that allows us to obtain phase pure crystalline zeolite for a zeolite, and we have a patent on this, and we used it for, in this case, for water absorption, with the idea of using the specific heat storage density for some applications. So I've shown you that geopolymers have intrinsic mesoporosity that can be exploited and modified. They have ion exchange capabilities, so we are applying them as filters and catalysts. Currently, we are working on removal of pharmaceuticals from water. We can further enhance and obtain hierarchical porosity, further enhance the behavior, developing hierarchical porosity by filler addition or in situ zeolite formation. And let me remind you that 3D printed parts have a better behavior, better mechanical properties, better permeability than other types of filters that you can think of. Another approach that we use for additive manufacturing approach that we use for manipulating for geopolymers, for printing components using geopolymers, is binder jetting. And in our case, we are using this approach where the part of the binder is present in the powder bed, and we spray a reactive liquid. So because of the reaction between the binder and the component in the powder bed and the reactive liquid, we form a bond in the powder bed, and the particles get bonded. So specifically, specifically we are using metakaolin in the powder bed, and we are using an alkaline solution as the reactive liquid. And if you're familiar with binder jetting, you know that the commercially available binder jetting printers, they use cartridges similar to the ones that you use for printing, inkjet printing, with a resolution of about 300 dpi. But you know that the nozzles are very small and they are very delicate. So you certainly are not able to use alkaline solution with this type of printing head. So we own a large-scale printer that has been developed by a company in Italy, which that was designed on purpose to allow for the use of alkaline reactive solution through nozzles, and this printer does not use inkjet cartridge, but it uses simply some nozzles with a certain size. And the advantage of this approach is that, again, we can use corrosive materials. On the other hand, being a large-scale printer, the resolution is low. So we use this printer for making components for applications that are different from the ones that I mentioned before. So the advantages of large-scale binder jetting is that it is fast for medium-large volumes. The printer that the company has a printer bed of 2 meters by 2 meters, and you can print up to 2 meters. You might say that this is not large scale, but then after printing, you need to move the part, you need to transport it, and 2 meters wide is the maximum allowed on a truck. So in Italy, so there is a reason behind that. And this is not this printer is not for building houses, okay? But it's for building large-scale components. The advantage of binder jetting is that you do not need support structures because the powder bed provides that for you. And also, since you are adding a binder in the powder bed, you can put whatever you want. And you can see what I mean by large scale. So you have the creation of the powder bed and the first layer. So we put the powder here, and then there is a semi-automatic deposition of the powder. Then we have the selective deposition of the activating liquid. And what we do is that we deposit half the thickness of the layer. We spray just after depositing, and then the rest of the thickness of the layer is deposited on top of the sprayed region. And we found that this is the best way of obtaining a layer which is a thickness of a few millimeters where the liquid is homogeneously distributed. In order to build large volumes, we need to have a formwork to contain the powder because you have the pressure, of course, of the powder bed. And then after printing, you need to remove the part and clean the part. You can see that the part is, the surface of the part is rough, but this is due to the fact that the resolution for this large scale printer is the pixel size is 5 millimeters. Our printer has a resolution of 3 millimeters. So this is our printer. So we can print 60 by 60 by 60. And you can see here the printing head. So this is the powder bed that contains metakaolin. And this is a series of nozzles that are jetting the liquid. And you can see also the speed at which this operates. So it's a very effective approach. This is the large scale printer. We worked on different projects with using this approach, and we have this solid binder, which is metakaolin, and which is highly reactive. I already told you the size of metakaolin powder, 6 microns by a few hundred nanometers. So very fine powder, like flour. And you know that this is non-flowable. So we cannot generate a powder bed by itself of pure metakaolin. But what we can do is to reduce the amount of metakaolin by adding fillers. And also the reason for doing that also is that metakaolin deriving from the decomposition of clay is more expensive than, for instance, sand. So we mix different aggregates with the inside our powder bed, but we still have the problem that we cannot have a lot of metakaolin because otherwise the powder bed will not be flowable. But I will describe you how we can solve this problem. So this is a way of this slide simply mentioned that we can use a wide range of aggregates and as a solid binder. We also used magnesium cement. We also used refractory calcium aluminate cement for making refractories. But here I'm talking mainly of geopolymers. And let me mention that because of the size of the nozzles, we can also not only have an alkaline solution, but we can also have a colloidal solution. And this helps in closing some of the porosity inside the printed part. So we can get a much higher density with respect to conventional binder jetting approaches. This is just some examples of printed parts. And these were printed at the company. Here, this is a reef that contains shells, residues that would have been discarded. And the idea is that they will favor the formation of new shells once put in the sea. We can also embed IT devices inside our printer part. This is in my department, and there is a system that monitors humidity, temperature, and other characteristics of the environment. If you go to Berlin to Jill Sanders' shop, you will find some tables that have been printed using by the company using this approach. This is a sound speaker shell. The size you can see here. And this is a sewage hub. Apparently, it's one of the expensive components that you have to generate using form specific molds that you had to make. But if you can 3D print the part, it will be much cheaper. So in our experiments, we used sand as an inert aggregate, but we can use waste. I will show you some examples of this. For one specific project, we needed to make the component more lightweight. So we added some porous materials like expanded glass, expanded clay, cenospheres, metakaolin. We use about 10 to 30%. We typically print using potassium silicate because it gives a higher strength. And this is how we solved the problem of being able of adding a non-small amount of small particles. So 38% of metakaolin binder. If you try to print it mixing it with sand, you obtain a particle bed that contains a lot of defects. And of course, all these defects will be present in the final part, reducing the strength. So what we did was to follow a granulation step using just a concrete mixer. We are able to coat particle sands with a layer of metakaolin. And in this way, we have coarse particles coated with the reactive particles that are loosely attached to the aggregate. And this allows us to spread even powder bed. And it has further the advantage that when the reactive liquid impinges, touches the particles, the metakaolin gets not just dissolved, but gets detached first from the sand particles and fills the voids, at least in part, the voids of the powder bed. And so you can see here the coated sand granules, and we didn't change much the size of the granules. And this is the powder bed. And if we add water, you can see that what happens is that the powder bed is very porous, but if we add the alkaline solution, the consolidated powder bed becomes much less porous. We go from a porosity of about 50 polypercent to a porosity of about 22% because of the formation of the gel and the detachment of the metakaolin from the supporting particles. So certainly you should ask, how can you form a geopolymer so quickly? Typically, in order to make a geopolymer, you work with it like if it was Portland cement. So you mix it with water or with alkaline solution. You mix it thoroughly, and then you have dissolution and condensation reactions occurring. Well, we found out that actually the geopolymerization reaction is very, very quick because simply by dripping the alkaline solution on the coated granules leads to the formation of the geopolymer. And we demonstrated that using aluminum mass spectroscopy, solid state mass spectroscopy. And you can see that this is these are the characteristic peaks for the metakaolin, where aluminum is sixfold coordinated. So it's not part, so it's in this form. but after reaction, it becomes fourfold coordinated, meaning that it becomes part of the 3D continuous geopolymer network. So the full geopolymerization has occurred. We also carried out, together with colleagues from INSA Lyon, in situ computed tomography studies of what happens when you have this reactive liquid entering the powder bed. And you can see here, this is the sand, this is the coating given by the metakaolin, and this powder bed has 55 volume% of porosity. And after, in the dry state, you can see all the black is the porosity. And after 3 minutes of the alkaline solution being dripped on the powder bed, you can see that everything is filled with a gel, and there is no significant further evolution of the microstructure, and the final matrix has, in this case, about 30 volume% of porosity. And of course, we dripped the exact amount of alkaline solution that we do in our printer. So this is a very effective method, and we also tested not just solid state NMR, but we carry out boiling tests. And if you have formed a geopolymer, then you have a 3D continuous network, and therefore the material is non-soluble. If you have an incomplete geopolymerization and you carry out a boiling test, the material will at least partially dissolve. And another way for checking that geopolymerization has occurred is by FTIR. And the band for metakaolin is around the silicon oxygen. Silicon band for metakaolin is about 1040, and if it is around 1,000 or below, then this is a confirmation of the generation of silicon oxygen aluminum bonds in the material. We tested the strength of the parts, and the material, as you can imagine, is non-isotropic, but the difference between the transverse and longitudinal strength was not too large. We bear in mind that I mentioned that we also use other binders. So, for instance, using a magnesium-based cement, which is fast setting, and it is a hydraulic cement, we are able to obtain the same results in terms of being able to print. But in that case, the part is much more anisotropic in terms of properties. And this better behavior is due to the fact that we have this 3D continuous network that embeds the entire part. But you can see still the presence of the layers that are visible after fracture. So in terms of aggregates, I'll show you that we have done different tests. And one project was to use thunderous sand, because sand, of course, is the most consumed natural resource on our planet. I think that I read that China in 1 year used the same amount of sand that in the US has been used in 10 years. So this couple of years ago. So the consumption of sand is a major problem, and the reuse of sand is something important. So we used thunderous sand for our experiments, and we had similar results in terms of properties. So we were happy with the possibility of using thunderous sand, which of course contains a lot of impurities, not just metallic impurities, but also phenolic resin impurities. Another work that we are carrying out is the use of waste material as a reactive source of alumina and silica. And one possibility is to use construction demolition waste, which has issues in terms of being used again in the building industry. And the characteristic of construction demolition waste is that, at least in our region, contains some bricks or brick fragments. And of course, you're familiar that bricks are made from clay, so they're based on a aluminosilicate composition. You're also familiar with the fact that they're fired at low temperature, around 880 degrees, at least in Italy, which means that you have still a large amount of reactive amorphous aluminosilicate. So brick residues work very well for making geopolymers. And you can use cleaned construction demolition waste, or you can use a regular demolition waste that contains also fragments of concrete. In that case, of course, you are diluting the amount of reactive material in the system. And so this on the left doesn't look very nice because we simply used as received construction demolition waste. But if we grind the material, then we can obtain better performance. So this is not great in terms of mechanical properties, because if you use metakaolin, you get much better properties. But it is a good way for recuperating some waste. And speaking of waste, one possibility is to use metallurgical slag. And of course, you can use slag from the steel industry, or you can use slag from other metallurgical works. And we had a project for using copper slag, which is basically based on iron oxide. And if you remember, and being a slag, of course, it's amorphous because it's extracted and cooled from the pot, from the reactor, and cooled quickly, discarded, cooled quickly. So there's a company in Sweden that makes a lot of this material. They sell it as a replacement for sand, but we wanted to use it as a reactive source of oxides that would enable the formation of a geopolymer. And if you remember, I mentioned that you can have iron silicate geopolymers besides having aluminum silicate-based geopolymers. So this material was milled below 100 microns to be more reactive. And we are able to obtain, to print and obtain a consolidated material. And we can also play a little bit more with the system. For instance, if you want to obtain a porous component, you can add something that can be later extracted and recuperated. So we added salt particles, and the salt particles do not dissolve quickly enough when we print, so they remain embedded into the printed material. And then after water immersion, they can be salt can be dissolved and can be recovered. You could think of doing this also with sugar, but sugar inhibits the geopolymerization reaction. So if you have a system containing sugar, which would be just as favorable in terms of occupying volume and then increasing and then eliminating it, you will not be able to geopolymerize. And the reason why, I mean, you could say, why are you adding something that you have to that you extract to make a porous material. Well, the issue is that the iron silicate has a high density, and we know that, of course, we have residual porosity in the printed part of about 30 to 40 volume%. And this leads to a component that is too heavy for certain applications. So we try to make it lighter by using this approach. You can see the slag and the slag with the salt. And of course, if you increase the porosity, you decrease the strength. So you need to find a balance for that. One possibly interesting point about this type of geopolymer based on iron silicate is that if you heat treat it to 800 degrees, then you start forming magnetic phases such as magnetite. So you might consider using this material for other applications. So I think I will stop here, and then after the break, I will continue discussing additive manufacturing using geopolymers, and then we will transition to the last topic of the course, which is cellular materials.